In our last discussion, I was showing you how to use the cumulative standard normal table. I also introduced you some functions in Excel that allow us to work with normal probabilities and finding points in a normal distribution. And the next step is to transition, and I ended that last discussion talking about non-standard normal distributions. Those are normal distributions that have a mean of mu and a standard deviation of sigma. So I'm going to go ahead and just draw in the value of mu here in my normal curve. We typically think of these as the distribution of x's. We use a symbol z for standard normals. And I talked about how normal distributions can be made to look like, can be solved with standard normal distributions. And that's the traditional approach. Now, Excel has a couple functions, and I introduced them to you, the norm.dist function, the normal distribution function, and the normal inverse function, .inv, that can be used to solve standard normal distributions, but even better, they can be used to solve non-standard normal distributions as well. Very few things in life have a mean of 0 and a standard deviation of 1, so the non-standard normal distributions are much more common. As we go through this, however, I'm going to show you the traditional techniques where we change normals into standard normals, and then I'll show you how to solve them using Excel probabilities as well, or Excel functions as well. And in order to do that, let's start with a little review of our z distribution or a z table. So here I have a probability where I want to find the probability z is greater than the negative 1.20. You may hear my dog chirping in the background. I wonder what's going on. He's very upset that we have a greater than probability, because greater than probabilities are not cumulative probabilities. And so in order to solve cumulative probabilities, or in order to solve greater than probabilities, we have to first find the cumulative probability, the less than or equal to probability, and subtract them from 1. So let's pull in a z table, and I brought in the left-hand side of the z table. There's typically two pages. There's the negative side of the table, the left-hand side, and then the right-hand side, which is the positive. The negative 1.2 is the z-score that I'm working with in this problem, so I'm going to find it right here, the negative 1.2, and I grab that second decimal place, the negative 1.20, using this column, and I match them up, and I see a probability of 0.1151. That's not the greater than probability. That's the polka dots. That's the red dots. That's the less than probability. And so I need to be able to use that. And so what we do is we subtract that from 1. And so the probability z is greater than a negative 1.20 is 0.8849. And we can find the same probability, that 0.1151, using our Excel norm.dist function. We put in a value of the x, or the z value that we want to work with. We put in a value of mu, we put in a value of sigma, and then true is what gives us the less than or equal to probability. And so the norm.dist function is an alternative to the cumulative normal table. Now again, what I mentioned, we can put in values of mu and sigma right here. So it works for standard normal distributions, but as we're going to see in this lecture, it works for non-standard normal distributions as well. The other type of problem that we looked at, the standard normal problem, was to find a point in the distribution where I'm looking for a z value, and we know this thing's centered at 0 here. This is my z curve. Let's see if I can draw a z. There we go. Put a little dash in there. And I want the probability greater than z naught to be 0.8078. And so we have to figure out, in order to use our table, we have to figure out what's the less than probability. And so if the probability greater than is 0.8078, the less than probability is the other side, 0.1922. So when you look to the left, you see 0.1922. When you look to the right, you see 0.8078. That should tell you that you're going to be over here. This 0.1922 probability is going to be below the value of z naught. And that's what you need. You need a cumulative probability, because that's the number you're looking up in the table. So let's see if we can find the probability 0.1922. Let's see, where is it? Here it is, right there, 0.1922. It's in the 0.07 column. It's in the negative 0.8 row. And so my z-score is going to be, that's wrong. It should be a negative 0.87. Okay, That's not good. It should be a negative 0.87. And through the magic of a little editing and some PowerPoint changes, you can see that's exactly what you get, negative 0.87. So to solve probability problems, you look up the z-score and you find the corresponding probability, and then sometimes you subtract it from one, sometimes you subtract it from some others. We saw examples of that in the last lecture. When you're trying to find a point in the distribution, you eventually have to get to a less than or a less than or equal to, and that equal sign doesn't matter, so you can write it either way, but you need the less than probability. In this case, it's 0.1922. You look that up in the cumulative table, and there you go. Another way of doing exactly the same thing is using the norm.inv function. And we looked at this in the last video as well. So if you have questions about this, go back. I explained a little bit more detail last time. Really what we want to do is now use this and work with other normal distributions. So here's a good example. GPAs of students follow a normal curve or normal distribution with a mean of 2.8 and a standard deviation of 0.4. What proportion of students have GPAs above 3.02? What a weird number to be asking about, 3.02. And yet, there you are. So we want to think about it in terms of a normal curve, except now the normal curve that we're going to be drawing, we think of these as being x's. This is how the GPAs, x is GPAs in this question, and they're not centered at 0. That doesn't make any sense. They're centered at 2.8, and my pen's going to do its thing. So I'm going to draw 2.8 in the middle of the curve. That's what you should draw in the picture. And now you got to ask yourself, where's 3.02? Well, 3.02 is to the right. It's bigger than 2.8, so I'm going to draw it over here. And I want to know the proportion of students that have GPAs above, and so I'm going to shade out here. And so I want to figure out the proportion or the probability, and I can rate these questions, a proportion of all students that have GPAs above 3.02. Another way of asking the same question, what's the probability a randomly selected student has a GPA above 3.02? They both work. Probability of a single one, proportion of all. But we don't have a table for this. I only have the standard normal table, and so we need to make the x's, we need to take a look at this GPA distribution of x's through the eyes of its z-score. So we need to transform it or change it. That's the word we use, transform. It sounds so official. We need to make the x's look like or behave like the z's, and the way we do it is we do some math. Hey, that's fun. You probably saw this in your notes and you're like, oh, this is going to be terrible. I'm going to take, and all I'm doing here is I'm taking this equation and I'm applying it to both the x, I'm subtracting the mu, dividing by sigma, and I'm doing the same thing to the 3.02. I'm doing a little algebra here. My math friends tell me that that's okay to do that. Everything stays the same. In fact, I'll go a little further and I'll say this left-hand side, the x minus mu over sigma, that's the z-score. That's why we're doing this. We're trying to look at this through the eyes of the standard normal distribution because I have a table that will allow me to look up z probabilities. For the right-hand side, I take the 3.2, I subtract the 2.8, and I divide by the 0.4. And if you're sitting here thinking, aren't we just creating a z-score for the 3.02? That's exactly what we're doing. And what the math tells me when I take 3.02 and subtract the 2.8 and then divide that difference by 0.4, it tells me the 3.02 GPA falls 0.55 standard deviations above the mean. What I know and what you need to understand is every normal curve has the same probability when you go 0.55 standard deviations above the mean. I don't care if you're working with the GPAs that have a mean of 2.8 and a standard deviation of 0.4, or if you're working with the standard normal distribution that has a mean of 0 and a standard deviation of 1. When I go 0.55 standard deviations above the mean, this is the z distribution here, these two probabilities, whoops, oh, that was terrible. The probability above 3.02, the probability above 0.55, they're exactly the same. What's the point of all this? I have a table that allows me to look up the probability, the z-score at 0.55. Here it is right here. It's 0.7088. That's not the probability above. That's the probability over here. That's also the probability over here below the 3.02. So how do we solve for above probabilities? We subtract it from 1. And that's a traditional method of solving normal probabilities. You start with a normal problem, you change it or transform it, you make it look like, behave like the standard normal problem, you look up the standard normal probabilities into you show how good you've gotten or how proficient you've gotten at working with the z table. Or you could do this. Excel makes it easier. Finding that 0.7088, because Excel allows us to put in different values of mu and sigma. I know what you're thinking. This part here, that was good stuff right there. I really enjoyed doing. Said nobody ever. It works. You start with a normal, you change it to a standard normal, or use what Excel allows us to do. We put in a value of X. We're interested in the probability around the value 3.02. The mean is 2.8, the standard deviation is 0.4. When I hit true, or when I type in true here, which is the option we're always going to use, when I use true, it's going to give me the less than or equal to probability. This norm.dist, and with what I've got written here, it's going to tell me the 0.7088. You need to know to subtract it from 1. You need to know we're looking for a greater than probability here. So Excel doesn't automatically give you the answer, it just gives us an easier way of getting to the answer. Let's take a look at another one. Look at this one. What proportion of the students have GPAs between 2 and 3? Again, 2.8 is the mean, so I'll put that in the middle here. 2 falls over here. 3 falls over here. I was trying to do it quick, so maybe it wouldn't do that. This is the value 2.00. This is the value. We want the probability in between. We've seen in between probabilities before. We need the cumulative probability for the 3 minus the cumulative probability for the 2. Hey, here's a one. Here's one way of doing it. Woof. We can change it to z-scores. I'm doing exactly, and this should be the value 0 here, sorry. This is a z-score of -2. This is a z-score of +5. What I'm saying is a GPA of 2.0 falls 2 standard deviations below the mean. A GPA of 3.0 falls 0.5 standard deviations above the mean. I could go to my z table. I could look up the negative -2.00, get the cumulative probability. I could take the 0.50, get the cumulative probability, and subtract them. Or I can skip some of that and just go right to Excel. I can do the normal distribution function. I can say, hey, I want the cumulative probability above or below, the cumulative probability below the 3.00. Look, that's the GPA, that's the mean, that's the standard deviation. And then get rid of the cumulative probability for the other one. So much easier to use the normal distribution function. I'm going to require it. When you do project work for me, you're going to have to use the normal distribution function to get your answers. So get good at it now. Try solving normal distribution probabilities using the norm.dist function. The other type of problem is, and this one's going to be a fun problem, the GPAs of students follow normal distribution, mean of standard deviation, mean of 2.8, standard deviation 0.4. Same beginning. We want to place the lowest 9% of students on academic probation. So this is one of those problems where I'm not telling you the GPA. In fact, I'm asking you to find the GPA that identifies a probability that I'm telling you about. These are the GPAs. They're piled up. They're centered at 2.8. Where are the lowest 9%? Aren't they going to be over here? Aren't the lowest 9% going to be in the left-hand tail? We now call this X naught, and we know that this probability here is 0.09. Now, if I'm using the standard normal table, I need to think about this as a 4-digit decimal. So let's put some stuff up here. The probability a GPA is less than X naught is 0.09. I'm going to change that to a z-score. That's how we solve that. And I'm going to go a little quickly here because I have a better way. I have an Excel way that's going to make your life easier. Remember what I said, my love-hate relationship with Excel? This is how we used to solve it. We would take a normal problem, right? We take the problem where I'm looking for the lower 9%. We would apply the standard normal transformation, and I would take and subtract mu, divide by the standard deviation on both sides of this equation. That keeps the probability intact. That gets me here, which gets me to this picture. I just transformed it to a standard normal. What that tells me is you have 0 in the middle. You have this point. I'm not even going to try to write that with the mouse. I'm going to take that X naught minus 2.8 divided by 0.4. That's the value right here. And I know this probability is still 0.0900. Now you go to your table, and we got to figure out what is this X naught value. Well, I can find the 0.0900. Where is it? 0.0900. 0.0900. It's about here. It's pretty doggone close, 0.09. It happens. What I'm saying is this point right here, the x naught minus 2.8 divided by 0.4, is the z-score negative 1.34. The point I'm interested in falls 1.34 standard deviations below the mean. That's what that information tells me. So now I got to solve for x naught. Turns out you solve for x naught, it's mu plus z naught times sigma. It's mu plus z naught times sigma. The mean and standard deviation I told you up here, 2.8, 0.4. I'm looking for the place or the value of x that is 1.34 standard deviations below the mean. I'm looking for this number right here. That's the GPA that identifies the lowest 9% of all student GPAs. Start with a normal, change it to a standard normal, get your standard normal answer, and now I got to change it back. I got to untransform it. It's a great problem. It's a great problem. I love finding points in the distribution. I really love it now. Excel gives us a really easy way of doing this. If we want to find the lowest 9%, we go and we use the normal inverse function. We put in a probability, the lower probability, the less than or equal to probability is 0.09, and I put in a value of mu and sigma. Not 0 and 1. That works with standard normal distributions. The mean in this case is 2.8. The standard deviation is 0.4. Now, one caveat, and when you type in equal norm.inv and then do the 0.09, 2.8, 0.4 and hit enter, it's going to give you 2.264. And again, it'll probably give you 2.26389 to 52 decimal places, but it's going to give you the answer. It's really a great way to find probabilities. No, I shouldn't say that. Find values in a distribution based on cumulative probabilities. The caveat is just be careful what you use for the probability. If I ask for the upper 9%, if I want to identify the highest 9% of students and say, hey, you're doing a great job, think about the picture, right? It wouldn't be on the left-hand side, it'd be in the right-hand side up here. I'd have 9% in the upper tail. What would the probability be that I'd need to put in the normal inverse function? Well, the normal inverse function is always working with cumulative probability. So if I was looking for the upper 9%, I wouldn't put 0.09 in as the probability down here. I would actually put 0.91. I would give the lower probability. You always have to work this normal inverse function in terms of the cumulative probability. So it is something to consider. But the normal.dist function is the best way to solve normals probability problems. The normal.inv function is the best way to find points in the distribution given probabilities. Let's take a look at another example. The amount of soda poured into a 12-ounce can follows a normal distribution with a mean of 12.05 and a standard deviation of 0.025. So 12.05 is right here. These are my soda amounts. What percentage or what proportion of the sodas contain less than, so 12 is going to be over here to the left, what proportion contain less than 12 ounces? Now, some of you guys might see the math. If I wanted to take the traditional approach and change these to standard normals, you might even be able to see, look at the math here. I got 12.05, I got 0.025, not a nice number, and I have 12. Can you see that the value of 12 ounces, the value I'm asking about, falls 2 standard deviations below the mean? The z-score is going to turn out being -2. So if you go that route where you start with a normal, start with the probability x is less than 12, do the z-score transformation, you're going to get here. You're going to get to the probability z is less than a -2.00. Now, you might see that, you might not, but what my point is, you don't need to see it. But you do need to be able to solve it using the distribution function, the normal distribution. Put in the value of x that you're interested in. I'm interested in the 12 ounces. Put in the value of mu, put in the value of sigma, and actually there's another piece here. I didn't put it in here, I should have. This is a mistake. And actually we're going to see the magic of editing once again. I need like a ta-da! I got to put the true in there. when you're using the normal distribution function, you need to put true or false, and we always use true. True gives us less than or equal to probabilities. Now, this probability is the answer in this case because it's a less than probability. If it was a greater than probability, I'd have to subtract it from 1. So you need to be able to work with the DIST function, and I wanted to make sure you saw the right form of it. The second part, and that z-score, you know, what do I need? You don't. If you get used to working with Excel, which I really strongly recommend you do, you only need the normal distribution function, and then in part B here, spillage occurs, and that's way too much. Spillage occurs, again, let's edit a little bit. Better. Spillage occurs when too much soda is poured into the can. What size soda, or what size can should be used? Only 6% of the can suffer spillage. So here's the pour amounts. They're centered at 12.05. So this is the amount of soda that's poured into the can. Whoops, I should say X. I only want 6% of the cans to be over poured. So you can think about it two ways. 6% of the cans get too much soda, 94% can hold the soda. So 6% are problems. Those are going to be out here where you get too much soda poured into the can. 94% are on this side. So you need to split, and then you got to figure out, is it a left or right? This is a tough problem because it's not as obvious. If I say find the top 6%, okay, that's easy. If I say find the bottom 94%, that's easy. But you got to think, what's spillage? Spillage happens when too much soda is poured into the can. It's going to be when the soda amount, which is the value of X, exceeds the can size, and we want that to be the 6%. That's what puts us over here on the right. And so I go to, and again, oh my goodness. Oh no, in this case, I don't need true. I thought I screwed up again here, folks. It's been a rough day. The normal inverse function doesn't require a true. It automatically makes us work with cumulative probability. That's why I had to take that 6% and make it 0.94. Put in the value of mu, put in the value of sigma, and it tells me the can size. If I'm looking for the bottom 6%, I would use 0.06, but because I'm looking for the top 6%, the cumulative probability is 0.94. So here's the deal. You need to get really good at working with normal probabilities. And most of the time you're going to be working with non-standard normals. You're going to have mu and sigma. It's not going to be 0 and 1. It's going to be 12.05 and 0.025, or it's going to be 2.8 and 0.4 like in the last problem. You have to get really proficient at working with the normal.dist function in Excel and the normal.inv. When it's the INV, you need a cumulative probability. You need a value of mu and sigma. If it's a normal distribution function, you need a value of X that you're interested in, value of the mean and the sigma, and then that true. Our next step is to ask the question, how do I know when I have a normal distribution? And that, my friends, is for another time. So I'll end the video here, get to work on normal distribution, normal inverse functions, and when you have questions, reach out to us. We'll be happy to help. So long.